looking at 3 examples in order to increase your knowledge on 4.4 and the optimization problems. These are all from our notes, and the first one I will be doing will be the answer or the concept of drawing another cylindrical can. Now in this case, the volume is 10 cubic feet, and we want to use the least amount of metal. Now, a couple things we're given with this. One, we have our volume given as 10 cubic feet. The volume of a cylindrical can, of course, is pi r squared. H is equal to 10. Since we are using the least amount of metal to construct this can, that is surface area. Again, 2 circles and a rectangular piece. We want to use the least amount of material, so we are going to minimize this. So I am going to take the direct derivative of my surface area. Of course, same problem. It's a 2-variable concept. That doesn't help. So I need to get one of those variables out, and that's why they give me this other equation located here with the volume. Again, easier to take out h. Rewrite that equation. H is equal to 10 divided by pi r squared, and make the substitution. My surface area formula is now a single variable. 2 pi r squared plus 2 pi r h, which has been pulled out. Clean it up a bit and get ready to take the derivative. Since I am minimizing this area, I am looking for a horizontal or any sort of cusp. In this case, taking the derivative, setting it equal to 0. Again, I choose to clear the denominators as opposed to getting a common denominator. Here is one of my critical points. R squared is equal to 0, which means R is 0. The other one, cleaned up after I multiply everything by R squared, gives me this cubic equation. Solve for R, and of course I get the goofy answer of the cube root of 5 over pi. Now, because of that particular answer, I can certainly use that and write it as a decimal answer, or I could use it and label it as A, as I did in the class notes. Continuing on with that process, let's look at the second page of this problem. I know that the can have an unlimited radius, and there's no end to it. Using that 0 that I got from clearing the denominators and the other value, I end up getting this particular one that says that this is a negative slope, this is a positive slope because of that equation. That equation came from the previous page. That's what gave me this answer. It is a minimum. Now, when I check my endpoints, I have one endpoint that r is equal to 0. That is a negative slope, so that point starts up and goes down, which means r would be a max. Now again, theoretically that makes sense. Radius can never be 0, but as my radius gets smaller, smaller, and smaller, my height would grow astronomically using more and more material to cover all that height. Just like on the other end, as your radius increases in size without bound, you can see from this positive slope located that it's telling you that your amount of material is just going to keep increasing, because now you're going to have a very wide can as opposed to one that was very tall. I could have also shown it was a minimum, of course, by doing the second derivative test. It's not too bad giving my first derivative equation. So take the second derivative, gives me this problem, plug in my value that I think is a minimum value into this equation. I get something kind of goofy, 4 pi plus 37.987. However, that is a positive number. Because that is a positive number, it is a minimum. So, the radius is the cube root of 5 divided by pi, which gives me this many feet, 3 decimals. My height came from going back to my height equation, which was given as over here, as 10 divided by pi r squared. Plug that value in, and I get the answer of 2.355 feet. And that allows me to then answer this question, that what is the least amount of material that I could use it would be a can with a radius of 1.168 feet by 2.355 feet. And there is one extra problem.